Since probability is so essential to quantum mechanics, it's good to go back and review to make sure we're all on the same page as far as probability. The fundamental concepts of probability, aside from probability itself, are probability distributions and what their properties are. So let's review probability. There are two main kinds of probability, discrete and continuous. Discrete probability is what you get if you have only a specific set of outcomes. Sort of, well, hence the word discrete. You have a discrete set of outcomes. And these outcomes can be anything. They can be the outcomes of a measurement, they can be responses in a survey, they can be any sort of data set. For example, if this is your data set, 0, 0, 1, 1, 1, 2, 2, 3, 4, 5, 2 zeros, 3 ones, 2 twos, and 1 each of 3, 4, and 5. For instance, suppose you go out and you ask 10 members of the general public how many sexual partners they've had. You might get a data set something like this. The way to think of this in the context of a probability distribution, well, I like to plot things. So let's make a plot of this probability distribution. We have our outcomes, 0, 1, 2, 3, 4, and 5. Down my axis a little there. We have 2 people who answered 0. So if we make a y-axis here, 1, 2, I can put a bar here at 0 that goes up to 2. There were 3 people that answered 1, so I should make a bar that goes up to 3 above the 1. 5, 3 above the 1. Likewise for 2, there were 2 answers for 2, and there were 1 each for 3, 4, and 5. 1 there, and 1 there. Now, our probability distribution looks like this when you plot it. What are we actually plotting here? We're plotting the number of people who responded for each particular answer here. We can make a table then of the probabilities. Either we have, on the left we have the value, and on the right we have the probability. Now what is the probability under these circumstances? We have a discrete set of outcomes, 6 different numbers, 0 through 5, and the probability of, say, 3 is just the number of 3's that appear in this data set divided by the total number of entries in the data set. So, for instance, if I want to know the probability of the value 1, well, there were let's start with 0. If I want to know the probability of the value 0, there were 2 respondents, so that would be 2 divided by 10. 2 people out of 10. So if I chose one of these at random, not looking at the numbers, the likelihood that I would choose 0 is, well, 2 out of 10. 2 times in 10, I would choose a 0 probability, on average. And you can do the same thing for 1, 3 out of 10, 2, 2 out of 10 again, 3, 4, and 5, all 1 out of 10. And some things you should notice about this, let me move it up slightly, to move everything up. The numbers here, if I add these up, 2 plus 3 plus 2 plus 1 plus 1 plus 1, it adds up to 10 out of 10. So the total probability of drawing any number is 1, and that is sort of a certainty. If you draw a number, you will draw a number. So if you only have a discrete set of outcomes, for instance, the integers like this, you're dealing with the discrete probability distribution, and the sum of the probabilities in a discrete probability distribution have to sum to 1. And it's a straight sum if I add up these numbers. The other class of probability distribution is a continuous probability distribution. Continuous probability distributions are what you work with when you have a range of values. A range of values, not a list of values. So for instance, suppose you got this set of numbers. This might be what you would get if you talked to 10 people who had just gotten off the phone with Comcast tech support and asked them, for instance, how long did Comcast put you on hold, say in hours. We can look at this probability distribution graphically as well, only it's slightly more complicated. Suppose the x-axis now here is my time in hours, and I have 1 and 2 to give a scale on my axis. Now if I plot this data set, I've got one at like 0.7 or 0.07, one at 0.11, one at 0.23, 0.55, 0.79, 1.09, 1.7, probably about there, 1.8, 1.88, and 2.16, something like that. So these discrete answers, each answer here is only a specific number on this axis. So if I want to make a meaningful plot, I can either pretend that my probability distribution is discrete, or I can attempt to guess at what the probability distribution looks like. Since I know what the answer is here, let's call this rho of x is typically the name given to a continuous probability distribution, and it would look something like this in this case. So we have what's called a probability density function, or just a probability density, rho of x. Now the reason we have a probability density like this, rho of x, is because x is a continuous variable now. It can be anything, in this case, say from 0 to infinity. What does that mean? If I evaluate rho of x at, say, x equals 1, you might think, well, okay, that's the probability of 1. But, well, one of the three fundamental facts of continuous probability distributions is that the probability that x is exactly equal to 1 is going to be 0. The example given in the text is, suppose you walked up to a random person on the street and asked, is your age 18 years, 3 months, 12 days, 18 minutes, 16 seconds, 52 microseconds, etc. If you precisely specify the exact answer you want, the probability that you'll get that exact answer is going to be 0. The only reason, or the only way that makes sense for a continuous variable or continuous probability is for the probability to be specified between limits. Suppose I had A and B, and I want to know the probability that the number that you're drawing from this distribution, or the random probability of amount of time that you would like to have to spend on hold with Comcast between, say, 45 minutes and an hour and 45 or an hour and a half. You could calculate that knowing this function, and the way you calculate it is by integrating. Put mathematically, the probability that, say, x is between a and b is the integral from a to b of rho of x dx. You can think of this more or less as the definition of the probability density function. If you have a way of calculating probabilities for x's and ranges, that is the probability density function. Probability density functions also have to sum to 1, but instead of having a sum, in the case of a discrete probability distribution, we have an integral. So the other property here is that the integral from minus infinity to infinity, the entire possible range of values, rho of x dx, has to equal, not 0, has to equal 1. The answer, the question that this equation here answers is, what is the probability of drawing a number in between negative infinity and positive infinity? And that had better be unity. This is the equivalent of the sum of the probabilities in a discrete probability distribution being equal to 1. Now, in this case, the probability distribution, to give you a feel for what these things look like, rho of x in this case is 0 if x is less than 0, and is equal to e to the minus x if x is greater than or equal to 0. So this is an example of a probability distribution function, or probability density. That's actually the distribution I used when I drew these numbers. So that's continuous probability. If you have a continuous range of outcomes, you have to deal with probability distributions and your probability density functions, and you have to do some integrals if you want to calculate properties. Now, what are those properties? Well, the most basic properties that you can think of is probably the most likely outcome. Now, in the case of a discrete probability distribution, this is just the most probable. What that means is that you've got the highest probability. And in this case, that means it's just the outcome that occurs the most times. In this case, 1. So our most probable outcome here is 1. In the case of a continuous distribution, it's slightly more complicated. If I plot the distribution function from before, the exponential, turn off the ruler. If I plot the probability distribution from before, looks something like this. The most probable is actually going to be 0. Now, you might think, what are the odds that Comcast puts me on hold for 0 minutes? Well, 0. That's our rule that the probability that x is exactly equal to 0 is 0. It only makes sense to make a statement like the probability that, say, x is greater than 0 and x is less than, say, 5 minutes. And that you can calculate with your integral, like on the last page. But in the case of the most probable value, the peak of the distribution is indeed 0 here, in spite of the fact that 0 will effectively never happen. Any exact value will effectively never happen, but 0 is the most likely. The next property is the median. Median is not something that appears very often in physics, but it appears a lot in statistics, so we need to mention it. The median is essentially the middle of the data set. So you've got half are smaller and half are larger than the median. So here I have 10 numbers. The median is going to be something that falls in between 1 and 2. Half the data set, 0, 0, 1, 1, 1, is smaller, and 2, 2, 3, 4, 5 are all larger. Typically what statisticians do when they define the median here, when there's no exact number that is the median, is to just put it halfway between the numbers. So in this case, the median would be 1.5. In the context of a continuous probability distribution, the median is the number such that your probability adds up, or the probability adds up to a half. So if I integrate from minus infinity, the lower possible limit that you could possibly have, up to the median, rho of x dx, I would get 0.5. So in the case of this probability distribution function, e to the minus x, I can write that out. This is integral from 0 to, I'll just call the median m now. E to the minus x is rho of x dx. Now I constructed this integral from 0 to m instead of from minus infinity to m because this probability distribution is 0 for x less than 0, just to make sure that it's clear why I used 0 here. And that's not actually a 6, that's a 0. So if you do this integral, you know the integral of e to the minus x is minus e to the minus x. Hopefully. If you don't, you need to review some calculus. There will be a lot of integrals like this in quantum mechanics, evaluated between 0 and m, and that has to be equal to 0.5. Plugging in the limits here, you get, well, I'll just simplify it and skip a step here. You get 1 minus e to the minus m equals 0.5, which if you solve it for m, gives you that m equals the log of 2. Now, if I get sloppy and say log here, I really mean natural log. Log, if I ever need a log base 10, I'll write log base 10. Most of the time we'll be using natural logs in quantum mechanics. So that's the median. The next property, and this is one that will be very common, is the mean. The symbol that we use for the mean is mu, and in the case of a discrete probability distribution, mu is the sum over all of your outcomes of the outcome, x sub I, times the probability that, say, x is x sub I. Sometimes this is just written as the probability of x sub I, which makes sense in the context of a discrete probability distribution. So what this looks like in the case of the discrete probability that I gave you earlier is, well, there's 0, that's x sub I, times the probability that x equals 0, which was 2/10, plus 1, that's x sub I, times the probability that x equals 1, which was 3/10, plus 2, x sub I, times probability that x is equal to 2, which is 2/10. And you can keep going, plus 3 times 1/10 plus 4 times 1/10 plus 5 times 1/10, for 3, 4, and 5, all of which have probability 1/10. And if you run through the numbers, you'll find this is equal to 1.9. If you remember from an earlier class that the mean is the sum of the values divided by the total number of values that you added up, that's the same formula as this. If you, say, factor the 1/10 out, all of these numbers have a 1/10, and if we factor that out, we'll get 0 plus 0 plus 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 4 plus 5, which is what you would get if you added all this up. And you get the same answer. So there's no black magic there. The reason I'm writing this way is this format here, where you have something times the probability of that something is something that shows up repeatedly. In the context of a continuous distribution, for example, the mean mu, now instead of a sum, we have to have an integral. And instead of a sum over all possible values, we'll have an integral over all possible values, minus infinity to infinity, of x times the probability density, rho of x dx. Now if I plug in this example, we'd be integrating again from 0 to infinity, so that I don't have to worry about, if I integrate from minus infinity to 0, the probability density is going to be 0 for that entire range. So I can ignore that and just start my integral at 0. And then I would have x e to the minus x dx. Now whenever you see an integral like this, hopefully you think integration by parts. The way I like to do integration by parts is to try and figure out, probably just by trial and error, which pieces of this equation are going to become which of the parts that I'm going to use. In this case, let's say u equals x and dv equals e to the minus x dx. Now, you differentiate this, du equals dx, and you integrate this, v equals minus e to the minus x. Now in integration by parts, the forms that don't have any differentials in them, that's your leading term. So we would have this integral is equal to x e to the minus x with a minus sign, evaluated at the limits 0 and infinity. Then we have a minus sign, and the integral part of the integration by parts result, which are these bottom pieces. So the integral now of e to the minus x with a minus sign, so I'm going to change this minus out front into a plus, and then this part just dx, from 0 to infinity. Now, what do we do with the endpoints on this? Well, at infinity, e to the minus infinity, that's 1 over e to the infinity, that's 0. And that's a really emphatic 0 if you think about it in the context of a limit. The limit as x e to the minus x of, the limit of x e to the minus x as x goes to infinity is 0. So our upper limit here is 0, and then we subtract what we get if we plug in 0 for this. Now e to the minus 0 is just 1, and x, well, x is 0, so we have effectively 0 minus a negative 0, 0 plus 0, whatever. It's still 0. This term vanishes. And what we're left with here is the integral of e to the minus x dx from 0 to infinity. And hopefully you know how to do that. That just, in the end, is going to equal 1. So that's our mean. Mean is also called expectation value, especially in quantum mechanics. It's not necessarily the value that you expect to get. It is it's this mathematical expression that tells you the value that is sort of in the middle of your distribution of possible values. The reason expectation value is perhaps a better term than mean, especially in quantum mechanics, is that we can apply it more easily to functions. For instance, f of x. The notation we use for the expectation value, or the mean value, of some function is to put that in brackets. So this is read as the expected value, or the expectation value of x, or perhaps just the expectation of f. Excuse me, f, not x. And this, in the context of a discrete probability distribution, looks a lot like the formula for the mean, except instead of x sub I in the sum, we have f of x sub I times the probability that x is x sub I. So suppose the function I wanted to work with was f of x equals x squared. What's the probability of x squared? Well, just applying this formula, you would have 0 squared from f of x with x sub I being 0 times the probability of 0, which was 2/10, plus 1 squared times 3/10. Now this is 1 squared times the probability of 1, plus 2 squared times 2/10, plus 3 squared times 1/10, plus 4 squared times 1/10, plus 5 squared times 1/10. And if you plug all the numbers in here, this is a fairly simple thing to do. Hopefully you can get the right answer on your calculator. It comes out to 6.1. To keep with my format from earlier, I should do this in color. The expected value of f is 6.1. You might also see this written as the expected value of x squared, just saving or compacting the notation a little bit and ignoring the definition of f. Same thing. For the case of a continuous distribution, the pattern by now is hopefully reasonably clear. The expected value of f in the continuous distribution case is equal to the integral from minus infinity to infinity of f of x times rho of x dx. And the integral in this case, for the example function here, is going to be equal to integral from 0 to infinity again, because rho of x is 0 for x less than 0. F of x is x squared, rho of x, e to the minus x dx. Now again, you see an integral like this, I want you to think integration by parts. Alternatively, I want you to think, oh, I should go plug this integral into Wolfram Alpha, or I should go look this up in a table of integrals, or whatever tool, if you have like a TI-89 or a TI-92, they can do integrals like this. Whatever technique you want to use to solve integrals is okay with me. But in this case, integration by parts will work, and it's not terribly difficult. So again, u is going to be x squared, and dv is, where's my eraser? dv equal to e to the minus x dx. Sorry, I'm running out of space there. Let me do this slightly more legibly. dv equals e to the minus x dx. Now, differentiate this. du equals 2x dx, and v equals minus e to the minus x. In our integration by parts then, the term out front, without the integral, is going to be x squared times minus e to the minus x, evaluated at the limits, 0 and infinity. And for the same reasons this term vanished in the last case, it's going to vanish here as well. If I evaluate this at infinity, this is going to be 0. If I evaluate this at 0, this is going to be 0. So this term will vanish. The second part of our integration by parts is minus the integral from 0 to infinity of, just for the sake of neatness, 0 to infinity. The parts here with the differentials in them. 2x dx e to the minus x with a minus sign, so I'm going to change this minus sign to a plus sign. This integral, I'm going to pull the 2 out front. 2 times the integral from 0 to infinity of x e to the minus x dx. And this integral, you hopefully remember because we just did it. This integral was equal to 1. That was what we did on the last page. So this overall is going to equal 2. So the expected value of x squared under this continuous probability distribution is 2. To check your understanding, here's a sample problem. The probability density function in this case, I'll plot it just to make things a little more intuitive. If this is 0 and this is 1 and 2, the probability density is 0 if x is less than 0. It's also 0 if x is greater than 1. And for x between 0 and 1, it's equal to 2x. So our probability density function looks something like this, and your task is to find the mean of x under this probability distribution, and the expected value of f of x equals the square root of x. So 2 tasks here to accomplish with this sample probability distribution. 0, 0, 1, 1, 1, 2, 2, 3, 4, 5. 2 zeros, 3 ones, 2 twos, and 1 each of 3, 4, and 5. For instance, suppose you go out and you ask 10 members of the general public how many sexual partners they've had. You might get a data set something like this. The way to think of this in the context of a probability distribution, well, I like to plot things. So let's make a plot of this probability distribution. We have our outcomes, 0, 1, 2, 3, 4, and 5. Down my axis a little there. We have 2 people who answered 0. So if we make a y-axis here, 1, 2, I can put a bar here at 0 that goes up to 2. There were 3 people that answered 1, so I should make a bar that goes up to 3 above the 1. 5, 3 above the 1. Likewise for 2, there were 2 answers for 2, and there were 1 each for 3, 4, and 5. 1 there, 1 there, and 1 there. Now, our probability distribution looks like this when you plot it. What are we actually plotting here? We're plotting the number of people who responded for each particular answer here. We can make a table then of the probabilities. Either we have, on the left we have the value, and on the right we have the probability. 2 times in 10, I would choose a 0 probability, on average. And you can do the same thing for 1, 3 out of 10, 2, 2 out of 10 again, 3, 4, and 5, all 1 out of 10. And some things you should notice about this, let me move it up slightly. Oop. To move everything up. The numbers here, if I add these up, 2 plus 3 plus 2 plus 1 plus 1 plus 1, it adds up to 10 out of 10. So the total probability of drawing any number is 1, and that is sort of a certainty. If you draw a number, you will draw a number. Now, what is the probability under these circumstances? We have a discrete set of outcomes, 6 different numbers, 0 through 5, and the probability of, say, 3 is just the number of 3's that appear in this data set divided by the total number of entries in the data set. So, for instance, if I want to know the probability of the value 1, well, there were let's start with 0. If I want to know the probability of the value 0, there were 2 respondents, so that would be 2 divided by 10. 2 people out of 10. So if I chose one of these at random, not looking at the numbers, the likelihood that I would choose 0 is, well, 2 out of 10. Since probability is so essential to quantum mechanics, it's good to go back and review to make sure we're all on the same page as far as probability. The fundamental concepts of probability, aside from probability itself, are probability distributions and what their properties are. So let's review probability. There are two main kinds of probability, discrete and continuous. Discrete probability is what you get if you have only a specific set of outcomes. Sort of, well, hence the word discrete. You have a discrete set of outcomes. And these outcomes can be anything. They can be the outcomes of a measurement, they can be responses in a survey, they can be any sort of data set. For example, if this is your data set,